Hello and welcome to Probability and Statistics. This is the first part where we will discuss probability basics, axioms, the conditionals of a probability, what are the specific conditions related to it, what is the probability also definition, independence, and Bayes' theorem. Definition of probability. Probability is a measurement of the odds or the likelihood for an event to occur, and it ranges from 0 to 1, 0 being an impossible event and 1 being a certain event. Like when we say it's 0% or 100% most likely to happen. Of course, when we talk about an impossible event, we're talking about this realm, this dimension here, in the natural, because you have multiple other dimensions. Okay, you have multiple other dimensions. This is, by the way, I'm reminded by something, and like God spoke to me concerning that, but it was also mentioned by Dr. Kevin Zaydai, so I'm not sure if I learned it from him first or but it was like confirmed to me, okay, or if it was revealed to me also when he mentioned the 7 manifold spirits of God. It's not the 7 spirits of God, 7 manifolds, meaning that there's only one Holy Spirit that's in the Bible, and 7 dimensions, 7 perspectives to it. Completely true. Okay, now and for any probability between 0 and 1, it reflects a changing or a varying likelihood or probability. As an example, when you flip a coin, the probability of having a tail is given by the number of favorable outcomes, meaning, in other words, how many cases in which you get a tail when you flip a coin. There's only one tail, so you have one favorable outcome, okay? So in this case, you have only one tail that you would get because you have only one coin, divided by the number of total possible outcomes, which is how many possible outcomes you might either get a tail or a head. So you have 2 possible outcomes, okay? So you have only 2 possible, or overall of 2 possible outcomes, which are head and tail. So the probability of getting a head or a tail, it's the same here, okay, is equal to 1 divided, which is the favorable outcome, number of favorable outcomes, divided by total outcomes, which are 2 possible outcomes, equals 0.5 or 50% probability. How we get the 50%? You simply multiply the 0.5 by 100. So for the case of equal outcomes, in other words, meaning that you have an equal probability for each outcome to take place. Let's say we're talking about a die, okay? The die that they use in the roulette, in casinos, and things like that, okay? It is supposedly, let's say we're talking about a cubic die. You have the same probability for any of these numbers to be hit, okay, to be gotten when you throw the die. But when you have a die that has an irregular geometric shape, you would have a probability to get one number different or slightly bigger perhaps than the probability to get another number, because the other number, for the other number you need that the die would sit or would stabilize on a smaller base, which is most likely it will stabilize, if it's not cubic, on a larger base, okay, because for a larger base it's most likely that it would not fall another lap to its side, okay? So it would hold the ground for a larger base. Okay, here we're talking about equal probability for each outcome, meaning that for a die which has 6 numbers, 6 possible outcomes, each one has a probability of 1 over 6. Each number from 1 to 6 has a probability of 1, which is, this is the favorable outcome, divided by total outcomes, which is 6. So the probability of an event, again, is equal to number of favorable outcomes divided by the number of all possible outcomes. So as an example, if you're rolling a die, what's the probability of getting an even number? Here we define two sets. The space that holds all possible outcomes, it is called the space, which is like the set of all possible outcomes. In this case, for a die, it is from 1 to 6, not from 1 to 9. Okay? Just so that you would know, it is from 1 to 6. But let's say for another example, you have a die having 9 values. It would be from 1 to 9. Okay? It won't be cubic though. And the event that holds the favorable outcomes for which we get what we want, let's say, okay, from 1 to 9, we need to get 2, 4, and 6, okay? Which are what? These are the odd values. Okay, so it would be from 1 to 6 for a die without the rest of the numbers. So let me correct here. 7, 8, 9 won't count in that die example, okay? So all possible outcomes are from 1 to 6, 6 possible outcomes. And the event, so we're evaluating the probability in which we get even numbers. What are the even numbers from 1 to 6? They are simply 2, 4, 6. These are the favorable outcomes. What is the number of the favorable outcomes? 3. So the probability of getting the favorable outcome of even values, even numbers, is equal to number of favorable outcomes, which is 3, divided by total outcomes, which is 6, equal 0.5 or 50%. Set theory basics. Okay, so the probability is based on sets. Again, we mentioned the sample space, which is the set of all possible outcomes for a specific scenario, like when we're talking about a trial or an activity of throwing a die. All possible outcomes, which are the sample space, are the numbers from 1 to 6. And the events, which are the desired outcomes, we're evaluating the probability for a desired outcome, let's say for instance getting an even number. Okay, so events E are subsets of the sample space, which is a larger set. Key set concepts. Okay, you have a universal set, the sample space, S equal 1, 2, 3, 4, 5, 6 for a die, for rolling dice as an example. Subset, which is the event, is included within the space. Okay, so the desired outcomes are a subset of the entire space. You cannot desire an outcome which is not existing, which does not belong to the space itself. That would be ridiculous, okay? Because this is what the probability measurement is about. So, as an example, rolling an odd number, okay? In such case, okay, when we're talking about an odd number instead of an even number, you would get 1, 3, and 5, not 2, 4, 6. 2, 4, 6 are for the even number. Event union. Okay, this occurs when any of the desired events happens, meaning that you have two events. If either of them happen, that would be a great thing. So the probability in such case of either of them happening is equal to the probability of the first one plus the probability of the second one. Why? Which makes sense, because if either of the two I hit them, okay, so if I get the first or the second, it would be good. So the probability is the probability of the first added to the probability of the second. They add up to each other. Now, okay, let's start with A union B. What is the union? So these are events in A or B, or B. As an example, you have two sets, A equals 0 and 1, and B equal 1 and 2. Okay, A union B, A cup B, is equal to, so when we merge these two sets together, of course, we should not repeat the 1 because it exists in both sets. A union B is equal to 0, 1, 2, including all elements between the first set and the second set, without repetition, without repeating an element. So the probability of A union B, okay, or probability of A or B of getting A values or B values is equal to probability of A plus probability of B minus, because here we have an intersection, we have a common element between A and B, minus the probability of getting an element intersecting A and B, minus the probability of A, okay, enter B, which means what? A intersect B is this one here, because in both cases one belongs to A and at the same time B, so it should not be counted twice. Okay, so the intersection of events occurs when both events happen at the same time, like A equal 1, B equal 1. Okay, so these are events in both A and B at the same time. So A enter B is equal to 1. Hence, probability of A enter B is equal to probability of A multiplied by probability of B. In this case, we multiply, okay? We multiply the probability of A and the probability of B. Now, in case you don't have any intersection between A and B, let's say A is 0, 1 and B is 2, 3. You have no common values between A and B. In such case, no intersection, okay? No common values between A and B. So PA enter B. PA enter B would be 0. And in this unique case, the probability of A or B would be equal to the probability of A plus the probability of B. Because they are completely distinct. They are completely separate. There's no common values between them. Only in this case. Complement of an event. What is the complement? It is when everything happens except the event itself. In other words, all outcomes are received, okay, except those who are existing in the event. So the complement of an event when you are drawing balls, like you have green balls, red balls, and blue balls within a box, okay, and you are drawing. So let's say the probability, we're measuring the probability of an event when you draw a blue ball. Okay, you have blue, red, and green, correct? Okay, this is the event. When you draw a blue ball, we are trying to measure the probability. Now, the complement of that event is drawing anything but the blue ball, meaning it would be the probability of drawing green or red balls. Anything but blue. In other words, it is the opposite of the event itself. Okay, it is the complete opposite. It's called the complement of an event. So it is denoted by, let's say the event is A. AC, meaning the complement of event A, is equal to the space, the entire space, minus A, minus the event. So anything but the event itself, anything but the outcomes of the event. So green, red, minus all the blue balls, which is the opposite of an event where you want to measure how many blue balls and the probability of getting a blue ball out of the box. So this would be the total outcomes minus those within the event itself. Example, S equal 1, 2, 3, 4, 5, 6, A equal 2, 4, 6, correct? So what is the complement of A? It is anything but A. So what is left is 1, 3, 5, which happen here in this case to be the odd balls, the odd values, okay? Because in A you have all the even values, so the complement of A is the exact opposite, which is all the odd values that were not included in the event A. Disjoint mutually exclusive events, meaning these are the events that have nothing in common whatsoever. In other words, the intersection between them is zero. There's no intersection. There are no common values, common outcomes between these two events. So, in other words, also, these are the events that not only have nothing in common, but cannot occur together at the same time. So mathematically, A enter B would be equal to 0. Hence, the probability of A union B, which was equal to PA plus PB plus PA enter B, since PA enter B is equal to 0, because there are no commonalities, then probability of A union B would be equal to probability of A plus probability of B. This is what we call a disjoint mutually exclusive events for these two events, A and B. Example, A equal heads and B equal tails when flipping a coin share nothing in common. Okay, this is Venn diagram summary. You have in the union is equal, everything encircles A and B or B without the overlap. Meaning, in the union you have A plus B, but you have only the common part added once, not twice, without the overlap. Intersection equal overlapping area between A and B, which is the middle purple in the center. And the complement of A is anything but A, which is the pink part here. If this is A to the left, that would be the pink part, meaning anything but A, which is a part of B since you have an intersection. Okay, now, so as a review, for the complement first, the complement, the probability of a complement, which is like, for example, probability of the complement of A, is the probability of getting all the outcomes except for A. It is equal to, this is the inverse, okay, of the probability of A. It is equal to having all possible outcomes, which is 1, okay? 1 is simply all the possible outcomes become all the desired outcomes. So let's say you have 5 possible outcomes. These 5 become the desired outcomes divided by the possible outcomes, which is also 5. So you get 1, which is 100%, minus the probability of A, which is the probability of the event itself. This gives us the probability for the complement. Second, the union, okay, P, A or B, getting the outcomes of A or B, the probability for that is equal to probability for A plus probability for B minus the probability for A enter B, A intersect B. Now for this joint events where the PA enter B is equal to 0, probability of A union B becomes probability of A plus probability of B, because A and B would become exclusively, disjoint events. In other words, that would be the example where when you flip a coin, the head and the tail have nothing to do with each other, okay? So PA union B would be equal to PA plus PB. As a practice, given S equal from 1 to 6, okay, that's the space for a die, A equal 1 to 3, B equal 3, 4, find A union B, A enter B, and A and the complement of A. Now you can pause the video if you want to try to solve it yourself and then come back to the solution. Let's start with the first one. A union B. What is A union B? It is A plus B minus what? Minus the intersection between A and B. Okay, so you have in A 1, 2, 3, in B 3, 4. Okay, so A union B is A or B. What is A or B? It is either 1, 2, 3 belonging to A, or B, which is 3 and 4, minus the common repetitive value, okay, the common event, which is repeating. So among these 2, 3, you only need 1, okay, because it belongs to either. So you need to remove one of the 3s lest we have a repetition. So A union B is equal to 1, 2, 3, and 4 without the second 3. Now, A intersect B is the common value between A and B, which is 3. Okay, so you see, A union B is A plus B, which is 1, 2, 3, 3, 4, minus A intersect B, which is 3, so we've removed 1, 3. Now, the third question is the complement of A is anything but A. So the complement of A is, you have in A 1, 2, 3, correct? Complement of A is 1 minus A, okay, and the probability, sorry. is but in the set is S minus A. We'll get to the probability later. What is S minus A? It is 1, 2, 3, 4, 5, 6 minus 1, 2, 3. So you remove the first three elements and you are left with 4, 5, and 6. This is the complement of A. We're not talking about the probabilities yet. Now the probability of A union B, which is probability of A or B. Okay? Probability of A or B occurring. Meaning like you're throwing the die, let's say, it has from 1 to 6, okay? What is the probability of getting A outcomes? You have probability of A is equal to the number of favorable outcomes, which is 3, divided by the number of all possible outcomes, which is 6, correct? These are all the possible outcomes. Great. Now, probability of B is equal to, again, number of favorable outcomes, which is 3 and 4, so 2 outcomes, divided by the total number of outcomes in S, which is the space, which is 6. Okay, now, PA union B is equal to PA plus PB, probability of B, minus PA enter B. Okay, now, what is the probability of getting A enter B? Okay, probability of getting A and B at the same time. So it would be this 3 here. Okay, so it would be, or the intersection is this 3, which is 3 divided by 6. Okay, PA enter B is 3, not 3, sorry. Okay, it is the number 3, but the probability of getting this number 3 is 1 divided by 6. Okay, so PA union B is equal to PA plus PB minus PA enter B. Okay, correct? Enter B equal to 3 divided by 6 plus 2 divided by 6 minus 1 divided by 6, which is PA enter B. So we are left with 4 divided by 6, okay? Or 2/3. This is the probability, around 6.666%. Now you can get the same answer using a different, simpler way, which is simply probability of A union B is how many favorable outcomes we have for A union B. It is from 1 to 4. So it's simply 4 divided by total outcomes, total possible outcomes, which is 6. So 4 divided by 6 equal 2 divided by 3. And that's the final answer. The same answer we've gotten using the first method. Okay? Now, probability of A enter B, as we mentioned, is 1 divided by 6. Finally, the probability of the complement of A. Now, the probability of A intersect B is 1 divided by 6, which is, as we mentioned before, you have 3, that's the intersection, so it is 1 possible favorable outcome divided by all possible outcomes, which is 6, so 1 divided by 6. And finally, the complement of A is equal to, what's the probability for the complement of A? Let me erase it a little bit. Probability of complement of A given by 4, 5, 6, which is 3 favorable outcomes divided by the total outcomes, which is from 1 to 6 or 6, is equal to 1 divided by 2 equal 50%, which is half of the values, okay, half of the outcomes. Axioms of probability or Kolmogorov axioms. A probability P measures the likelihood of an event to occur with a value between 0 and 1. It has three fundamental axioms or rules, if you will. The first axiom, or axiom 1, is non-negativity, which implies that for any event A, probability of A is always greater than or equal to 0. It's always positive, whatever the value of A or the event A is. Axiom 2, normalization. The probability of the sample space, in other words, for any occurrence within the space, probability of getting any number between 1 and 6 when you throw a die which has values from 1 to 6 is 100%. It's certain that you'll get 1 or 2 or 3 or 5 or 6 when you throw a die. This is what it means. So the probability of the sample of getting any value within the sample is 100% or 1. As an example, let's say the space is head and tails, okay, for flipping a coin. Probability of getting a head plus probability of getting a tail, or in other words, probability of getting a head or a tail, which is mutually exclusive, meaning that you cannot get a head and a tail at the same time, is equal to 1/2 plus 1/2 equal 100%. Axiom 3, additivity for disjoint events. If two events A and B are mutually exclusive, A intersect B would be equal to 0, meaning there are no commonalities between A and B. So the probability of A or B would be like the probability of head or tail, equal to PA plus PB minus PA enter B, which is 0. So it is PA plus PB. Conditional probability. Conditional probability measures the likelihood of an event happening given that another event has already occurred. So, as an example, probability of A given B, this is how it's written. Probability of A pipe B means probability of A occurring given that B has already occurred, has already been satisfied, is equal to probability of A intersect B divided by probability of B if the probability of B is greater than 0. This is where it only applies. Now, probability of A given B reads probability of A given that B had already taken place. Example, again, rolling a die. Let A, first event, be the case where you only get even numbers, which are from 1 to 6, 2, 4, and 6. These are the values that respect having even numbers. As for B, this is the other event, which is when you get values greater than 3. So what are the different outcomes of that event that satisfy the condition of this event? It is 4, 5, 6. These are the values for which you get a number that is greater than 3. Then A enter B. What is the intersection between A and B? It is 4 and 6. Okay, these are the common values that are at the same time greater than 3 and even values. Okay, so these are the values that are at the same time greater than 3, which is for B, and even, which is for A. This is how you understand intersection. Now, the question is, what is the probability of getting an even number given that this even number is greater than 3? This is the probability, this is the event we're talking about, okay? So, what is the probability of getting A, which is an even number, given that this even number is greater than 3, which is in B, correct? So, PA given B is equal to PA, probability of A enter B, intersect B divided by the probability of B. Okay? So, of course, you can pause the video and try to solve it first. Alright. PA enter B is equal to number of favorable outcomes in this case, which is 4 and 6, divided by the entire space, okay, number of all possible outcomes. When you throw a die, all possible outcomes are from 1 to 6, which is 6 possible outcomes in total. Okay, let me rewrite that. So S, the space, is given by 1, 2, 3, 4, 5, and 6. Okay, so PA enter B is equal to 2 divided by 6. Now, probability of B, which is getting numbers greater than 3, is given by 3 favorable outcomes divided by total outcomes, which is 6. Okay, now probability of A given B, meaning probability of getting an even number given that this even number is greater than 3, is equal to PA enter B, which is 2 over 6, divided by PB, which is 3 over 6. Okay, 2 divided by 6 divided by 3 divided by 6 equal to third, and this is the final answer. Multiplication rule. Okay, directly from the definition, it is PA enter B, for instance. It is the probability of intersection, which gives you the multiplication. So PA enter B is equal to PB, probability of B, multiplied by PA given B. Okay, so it is the reversal of the equation here. Or PA enter B is equal to probability of A multiplied by probability of B given A. Okay, both of them apply. Independence. Now, two events do not influence each other if they are independent. In such case, PA enter B would be equal to probability of A multiplied by probability of B. Okay, so these two events do not affect each other. They are completely independent. Okay, it's like when you pour water into a scale. Okay, these two events, the scale moving and the water itself, affect each other. Why? Because when you pour the water in a bottle that is placed on a scale, the scale will move, will change, the weight will change. Okay, this would not be independent. But when we're talking about two completely independent events like throwing the ball and I don't know, collecting a coin, these are two completely different things, so they would not influence each other. Equivalent forms. Okay, so PA or like PA given B is equal to probability of A, probability of B given A is equal to probability of B. Example, flip two coins. A equal first coin is heads, so the probability of A is equal 1/2. B equal second coin is heads, probability of B also getting a head in the second coin is equal to 1/2, 50%. In either coin, you have two. The probability of getting heads is 50%, is 1/2. So A enter B, probability of A intersecting B is equal to HH, getting two heads, independent from each other. So the probability of A enter B is equal to probability of A multiplied by the probability of B is equal to 1 divided by 4, 1/4. Okay, so PA multiplied by PB is equal to 1 divided by 4. So A and B are independent. Bayes theorem and application. Bayes theorem relates conditional probabilities by reversing the condition. Okay, so you have probability of A given B is equal to probability of B given A, we reverse the condition, multiplied by probability of A divided by the probability of B. This is Bayes theorem, and we're going to see an application, an example for that to make it more clearer. So where P of A is the probability of A before seeing B, before knowing or assuming the outcome of B, PBA is the likelihood, okay? So probability of B given A, then probability PAB is probability of A occurring given B has already occurred. Okay, this is the expanded form here. But the thing is, probability of A given B is equal to probability of B given A multiplied by the probability of A divided by the probability of B. Example, a disease affecting 1% of the population, or in other words, the probability for having the disease is 1%, which is 1 divided by 100 or 0.01. Okay, now the sensitivity is given by, meaning that the probability of TT means someone testing positive. So he tested and the result of the test is positive. Probability of testing positive given that the person indeed has the disease, so we know he has the disease, okay, and he tested positive, is equal to 0.95. This is the positive rate. False positive rate, okay, meaning that the person has tested positive, meaning based on the test he has the disease. Meanwhile, okay, it is given, so in other words, meanwhile he doesn't have the disease. This is the complement of D, meaning he doesn't have the disease, he's not sick. However, he tested positive, so PT is given or written PT given DC, meaning it is the probability of testing positive given that the person is not sick, he does not have the disease. Okay, probability, of testing, yeah, positive, but it is a false positive, meaning that the test is false. It's given by 0.1. Okay, so if you test positive, that's T. What is the probability of having the disease given that you tested positive? This is the question. You can pause the video, try to think about it at first. Of course, we're going to use the formulas that we've seen previously in order to solve this dilemma here. Okay, so what we need is, we need probability of the disease intersecting the probability of testing positive, okay, probability of not having the disease intersecting testing positive, which is a false positive, and we evaluate PD given T. Okay, let's think about it for a while. So the point is getting the probability, the total probability of testing positive, whether false or true positive, whether we're testing positive but we don't have the disease, or testing positive and indeed the subject has the disease. Okay, why? Because we need the total probability of testing positive to place it within this equation, which is probability of disease given that a person has tested positive is probability of D enter T intersect T, probability of having the disease, intersecting probability of testing positive, divided by probability of all positives, whether false or true positives. Now, probability of having the disease intersecting the probability of testing positive. Okay, so probability of having the disease and being positive, this is how you read it. It is given by PD enter T equal to the probability of, here you reverse it, it is the probability of testing positive given that you have the disease multiplied by the probability of the disease. Okay, see, we've reversed it. Actually, the original formula is probability, let me rewrite it to make it clear. Okay, so probability of T given D, of testing positive given that a person has the disease, is equal to probability of D enter T, so you flip it, divided by the probability of the disease, of someone having the disease, which is 0.01. We already have this one. Okay, so let me continue. Okay, so probability of D intersect T is equal to probability of T testing positive given that a person have the disease multiplied by the probability of the disease. Again, we derived it from this formula. Okay, probability of T given D is equal to P probability of D enter T divided by probability of the disease. Equal, okay, so probability of T given D is here 0.95 multiplied by probability of the disease, which is 0.01, which is 0.0095. Great. Now, let's measure the probability of testing positive while not having the disease, which is a false positive. Okay, so probability, not while, meaning probability of not having the disease and testing positive. So it is probability of DC, which is the complement of D, enter T, is given by. Here you flip it again. So since we have this value already, it is probability of testing positive. You see, we reverse the order. Given that we don't have the disease, multiplied by the probability of not having the disease. Okay, PT given DC is equal to 0.1 multiplied by the probability of not having the disease. What is the probability of not having the disease? It is simply equal to 1 minus PD, minus the probability of having the disease. It is the inverse. So it is equal to 0.99, which gives us 0.099. Okay, so we've gotten these two values. Hence, the probability of testing positive, whether false or true, is the sum of these two probabilities. So total probability of testing positive, let me erase these values here, okay, these dashes. Probability of testing positive is equal to probability of being diseased and testing positive plus probability of not being diseased and testing positive, which makes sense. Okay, it is probability of testing positive given that you are diseased plus the probability of testing positive given that you are not diseased. This is the total of positives, whether false or true. It gives us the total of positive results. So we've gotten this value. Now, since we have PT, what can we get from that? So going back to the question, probability of D given T, probability of having the disease given that we tested positive is equal to probability of T enter D, correct? Probability of testing positive and being diseased divided by probability of testing positive. P, probability of having the disease given that we tested positive is equal to probability of the disease, okay, having the disease. And by the way, PD enter T or PT enter D, it's the same thing. So probability of the, having the disease while testing positive is equal to probability of the disease and testing positive divided by the probability of all positives, which is 0.0095, this is PD enter T, divided by the probability of testing positive, which is 0.1085, around 8.8%. Another example, a factory has 3 machines producing the same product, M1, M2, and M3. Now, the total production, percentage of produced items coming from M1 is 40%, meaning 40 out of 100 products come from machine M1. 35 out of 100 come from machine M2 and 25 out of M3. And if you notice, if we add all of these values up, they amount to 100. Okay? Now, out of these 40% of M1, you have 3% defect rate, meaning that out of 40%, you have 3 0.03 out of these 40s are defected. Then from the second machine you have 4% defect rate. So each 100 product you have 4 of them defect, and the third one, for each 100 you have 5%. Calculate the probability of defect. That's first. Then calculate the probability of the product coming out of M3, out of this machine, given that it is defected. All right? So you can think about it, pause the video, and get back after figuring out if you want. Let's start with the first question. So, calculate the probability of defect. Probability of defect is given by probability of defect given that the item came from the first machine, or probability of defect, or which means plus, adding to the probability of defect given that the item came from the second machine, or defect from given that the item came from the third machine. So how can we actually write that? This is given by simply probability of total defect is equal to probability of defect given that the item came from machine 1 multiplied by the probability of the item coming from machine 1, okay, in general, plus probability of defect given that the item came from machine 2, okay, multiplied by the probability of the item coming from machine 2, defected or not, plus PD given that M3 multiplied by M3. To give you a clearer perspective, so let's say, okay, probability of the item coming, being defected, okay, in machine 1, correct? Actually, yeah, probability of the item being defected given that it came from machine 1 is 3%, because 3% in machine 1 are defected, or 0.03, multiplied by the probability of the item coming from machine M1 is 40%, because 40% out of all of the products are coming from M1. So it is 0.03 multiplied by 0.4, which is 40%. Plus, notice something. Okay, probability of defect given that the item came from machine 2, which is 4%, okay, multiplied by the product coming from machine 2 in general, which is 35%. Again, the probability of defect, I'm sorry for like the previous part, the camera was blocking a part of the solution. So coming back to that, the probability for the defect is given by probability of defect given that the item came from machine M1, which is 3%, multiplied by the probability for the product coming from M1, which is 40%, 0.4. So it is 0.03 times 0.4 plus probability of defect given that the item came from M2, which is 4%, okay, probability of D given M2, multiplied by probability of the product coming from M2, whether defected or not, which is 35%, plus probability of D given M3, meaning probability of defect given that the item came from M3, which is here as clear as sun, as noonday, as they say, which is 5% multiplied by the probability of the item coming from M3, which is 25%. You add them up and you get 0.0385. This is the total probability of defect, whether it came from M1, M2, or M3. That's the total probability for defect, which will serve us in this equation here, in the second part. Now, probability of M3 given D is given by probability of D given given M3 multiplied by PM3 divided by probability of D. Let's get to that. Yeah. Probability, in other words, of the item coming from M3, given that it is defected, is given by probability of M3 enter D, meaning probability of having the item coming from M3 and being defected at the same time, divided by probability of defect, which we've gotten a moment ago, equal probability of D, meaning probability of defect, given that it came from M3, which is 0.05, multiplied by PM3, because PM3 enter D is equal PD M3, given M3, you see we reverse the order, multiplied by the probability of M3, okay? So this can be written, PD given M3 is equal to PM3 enter D divided by PM3. This is where we've gotten this formula here in the numerator, okay? The replacement of PM3 enter D. Okay, so PD given M3 multiplied by PM3. So probability of disease given M3 is 5%. It is in the table. Multiplied by the probability of the item coming from M3, which is 25% or 0.25, divided by the total probability of disease, which is this value, 0.0385, equals 0.3247 or 32.47%. Okay.